So I wanted to discuss more of an application domain, but there will be interwoven intersections with theories of high-dimensional statistics in this talk. So we'd like to talk about a theory of this neural dimensionality dynamics in measurement. So neuroscience is experiencing a very interesting time where we're experiencing our own Moore's law, which is an exponential rate at which we can increase the number of neurons we can record from the brain with a doubling time of about 7.4 years, right? So right now, we can routinely record from about 100 to 1,000 neurons, but mammalian circuits controlling complex behaviors contain many, many orders of magnitude more neurons, from 10 to the 6th to 10 to the 9th. So if we extrapolate this trend, we'd still have to wait about 130 years or so to get the requisite 5 orders of magnitude more neurons to record from the brain. So natural question is, are we in some kind of anti-Goldilocks moment? And essentially, there's a conceptual elephant residing within all of systems neurophysiology research, is which electrophysiologists, undeterred, still record from 100 neurons in circuits containing many more neurons and make scientific inferences. So the conceptual elephant is, why can we rely on these scientific inferences? And how would they change if we did indeed record all the neurons in a relevant circuit? Okay. So what's the kind of data that we're working with? So we directly collaborate with many neuroscience laboratories. So here's example data of 3 different neurons recorded from the motor cortex of a monkey while the monkey is reaching to various targets at 7 different directions at 2 lengths and different speeds. And as you can see, there's a lot of heterogeneity in this data. This data is averaged over many, many trials where the monkey performs the same reach. And there's about 100 more neurons like this in the data set. So how are such data sets analyzed? Principal components analysis and various other dimensionality reduction methods are used to analyze the data. And they yield often very insightful dynamical portraits of how the circuit computes. So these are the dynamics in the dimensionally reduced space. And we learn a lot. For example, here we learned that the locust olfactory system knows a lot about the identity of the odor in the transient dynamics of the system long before it hits the fixed point. In the monkey somatosensory cortex, the monkey encodes the passage of time as well as relevant information for the task. And this is the dynamics in motor and premotor cortex. And actually, if you record from the entire brain of the zebrafish, you can fit the dynamics into 3 dimensions. And actually, this is sort of a ubiquitous observation in neuroscience, is that even when we record from hundreds of neurons, we can account for a lot of variance in the data using a small number of dimensions. So all of this work raises several conceptual questions which we'd like to address. In a wide variety of neural recordings, the measured dimensionality is far less than the number of neurons. So what is the interpretation of this empirical observation? It suggests that there's an underlying simplicity to this data, and so what is its origin? And also, while we record from hundreds of neurons, there are many more neurons, for example, in primate motor cortex. So how would the dimensionality change if we recorded more neurons? How would the dynamical portraits, these low-dimensional neural trajectories, change if we record more neurons? Can we even trust them with such small numbers of neurons? And this is really a question that extends far beyond the RID of neuroscience. It's a question about what, if anything at all, can we learn about large dynamical networks at such an overwhelming level of undersampling? Okay. So just to give you some numbers, again, there's about 100 million neurons controlling 650 skeletal muscles in the primate motor cortex. These experiments have 100 neurons. The PCA dimensionality, or approximately what you need to explain about 70% of variance across all 8 reaches, so in a simple data set where the monkey's reaching to 8 directions, is only 7. The dimensionality required, I'll explain why I'm talking about 70% here in a little bit. The dimensionality required The dimensionality required to just explain a reach to a single direction is about 3.3. So the question is, where do these numbers come from? They're in some sense a fundamental description of the complexity of the data set, but we have no theory for why they take the quantitative values that they take. So we'd like to offer such a theory that answers this and the previous questions. So let me give you the take-home messages. So you may suspect that the complexity of the neural data is somehow related to the complexity of the task that the monkey is doing. So we pursued this idea, and the question is, how do we make this idea quantitative? So we came up with this new definition of neural task complexity that takes into account 2 distinct pieces of information, the complexity of the task and the smoothness of neural activity patterns. And then we proved a theorem that neural dimensionality must be less than or equal to our measure of task complexity. And when we re-examined the motor cortical data, we found that the motor cortical data was indeed as high dimensional as possible, or almost as high dimensional as possible, given this neural task complexity measure. This automatically has implications for neuroscience, right? It suggests that if you do future experiments where you repeat the same behaviors but record more neurons, you will not get a richer data set as quantified by the dimensionality, at least, of the data. And then we also looked at conditions for the accurate recovery of these dynamic portraits. And what we do is we come up with a novel conceptual connection between the act of doing electrophysiology and the act of doing random projections on the brain, essentially, on the neural circuit. And what we find is that the number of neurons we need to record should grow logarithmically with the neural task complexity in order to accurately recover these portraits. So this is fantastic news. These existing portraits are likely to be accurate despite recording so few neurons. And as we do go to more complex tasks, we don't need to record that many more neurons. Okay, so now let me fill all of this in mathematically. So I'll just give you some intuition behind this neural task complexity measure and why it's an upper bound of dimensionality. So imagine a simple example where a monkey is reaching to a certain target, so its arm moves from here to here, and neural activity evolves over time, and it's fundamentally a trajectory in a high-dimensional space. So it evolves over a finite extent, but not at infinite speed. There's an autocorrelation time. So the maximum number of linear dimensions this trajectory can explore is the duration of the trajectory over the autocorrelation time. Right? What about a slightly more complex task where you have both time and space? The manifold of task parameters is then also is parameterized by a cylinder. And what I said for time at a single angle also holds for angle at a single time. So as you march around this circle, the number of linear dimensions you can explore is 2 pi over a spatial correlation length. And then if we imagine that explorations across time and space are completely independent of each other, then an upper bound of the dimensionality would be the product of these two. And that's essentially the intuition. So neural task complexity is essentially the volume of the task manifold divided by a set of autocorrelation lengths across each task parameter. And our theory essentially provides a quantitative way to extract these correlation lengths and, most importantly, the proportionality constant, such that we can prove a theorem that the dimensionality of neural data is less than or equal to the minimum of this neural task complexity and the number of neurons where we record, where we define neural task complexity to be this participation ratio of the PCA eigenvalue spectrum. This participation ratio is a continuous function of the spectrum that is 1 if one eigenvalue is large and all the other eigenvalues are infinitesimal, and is n if all the eigenvalues are the same. And for a wide variety of spectra, it corresponds to about 70% of variance explained in the data. Okay, now I've given you just the intuition, but how do we actually mathematically prove this? What we do is we take the parameter by parameter covariance matrix of the neural data, and we systematically destroy structure in the data. And each time we destroy structure, we prove the dimensionality goes up. How do we destroy the structure? We first find the best tensor product approximation to the covariance matrix that factorizes across task parameters. That's how we get this product form. Then in each parameter, we find the best stationary approximation to the time evolution of the trajectory, or the spatial evolution of the trajectory. And we show that the best stationary approximation has higher dimensionality. And then at the end of the day, we characterize the autocorrelation by a single number, its width, and we get this result. Okay, so what are the implications for neuroscience now? So let's go back to the data. So remember, we had 109 neurons, and the dimensionality was 3.3 for a single reach and about 7 for multiple reaches. If we now compute the task complexity in this data set, it's 4.2 for a single reach and 10 for multiple reaches, right? So essentially, it's saying that we shouldn't think of these numbers as small because they're small compared to the number of neurons, but they're actually quite large compared to the simplicity of the task with which you probed the monkey's brain. This makes automatically two predictions. Okay, prediction one, if we vary the task complexity by varying the amount of time we include in our analysis, the dimensionality of the data should vary linearly with time if it hugs this upper bound. And two, if we just drop neurons in the data set, the dimensionality should remain completely unchanged because it's already upper bounded by this thing. So here's prediction number one verified. This is the dimensionality of the data set as a function of the amount of time, and we see a linear scaling with time that closely hugs the upper bound. And here we see that if we drop neurons, we essentially have no effect on the dimensionality of the data. Right? So, as a theoretical neuroscientist, our business is to make non-trivial predictions, so it's nice that these became verified. Okay, so basically the lesson for neuroscientists is now whenever we look at the dimensionality of neural data, we should compare it not to the number of neurons we record, but to this upper bound. And then from that, you can make scientific conclusions. If it's equal to the upper bound, then the richness of your data is constrained by your task design. But if it's less than that, and only if it's less than that, then you have discovered an intrinsic dynamical constraints in the circuit above and beyond those imposed by the task. Okay, but beyond dimensionality alone, what about the shape of these neural trajectories? So what are situations in which the resulting dynamical portrait obtained from dimensionality reduction, say through PCA, would be the same if you recorded 100 neurons versus 1,000,000 neurons, right? The simplest visualizable example is, let's say that you have a circuit with 3 neurons in it, and for whatever reason, your experiment yields neural activity patterns that are constrained on a one-dimensional manifold. If that manifold is randomly oriented with respect to the single neuron axes in a way that can be made mathematically precise but is not essential for conveying the intuition, if it's randomly oriented, then it doesn't really matter which 2 neurons I measure. The shadow of this trajectory onto the subset of recorded neurons will be the same, and its geometric distortion won't be too large. Of course, we may not always get that lucky in neuroscience. If we have a situation where a small subset of neurons is doing all the work, then we better record a large fraction of the circuit in order to see it, right? So in this crowd, I don't have to explain this any further, but in a situation where this manifold is indeed randomly oriented, then an act that neurophysiologists have been doing for the last 50 years becomes equivalent to a relatively modern technique in machine learning known as random projections. Basically, the act for recording from a random subset of neurons becomes equivalent to recording. So if you record from M neurons, the results that you get would be equivalent to what you would get if you recorded from M random linear combinations of all neurons in the circuit. That's an experiment we cannot yet hope to do, but under this assumption of a random orientation of the neural manifold, the results from these 2 experiments would be the same. So let's use random projection theory to compute how many neurons we need to record, and then test that prediction against the data. Okay, so we're just applying existing theory. So just to quickly review the theory of random projections. As usual, data live on interesting submanifolds in usually a very, very large ambient space. And a natural question is, if I randomly project the data onto a lower dimensional subspace, when will the geometry of the projection be preserved? Where the preservation of geometry is measured by the fractional distance, fractional error in pairwise distances measured in the low dimensional space relative to the high dimensional space. And there's various theorems that relate to sparse unions of subspaces, points, which would lead to the jail lemma. But what we're interested in is continuous manifolds. So there were some results by Baranyuk and Wakin that said that as long as the number of random projections is bigger than 1 over epsilon squared, where epsilon is some desired level of distortion, times the intrinsic dimensionality of the manifold, times the logarithm of the curvature times the volume of the manifold, then with high probability over the choice of random projection, the maximal distortion will be order epsilon. Okay, so the way this applies to us in neuroscience is this is the ambient, this ambient space is order of has a dimensionality order 100 million or so. This has a dimensionality that's quite small, as we saw, order 10. And this, we go down to about 100 neurons. And so we can compute, essentially, the distortion that we should expect to receive. And interestingly, the volume times the curvature essentially boils down to, if you translate into our notation, the neural task complexity. So essentially, random projection theory as a theory of neurophysiology makes a striking prediction. It says that the number of neurons should scale as 1 over this distortion squared times a logarithm of the task complexity. So how do we test this in neural data? What kind of analysis should we do? Well, we can't measure all the neurons in the brain for an infinite amount of time, but we do get a data set that sits here, which is the number of neurons we measured and the total duration of a reach, right? So what we can do is we can drop neurons and reduce the amount of time that we look. And if we drop them linearly in a space which is logarithmic in the time and linear in the number of neurons, then the isocontours of distortion should be straight lines in this plot. And if we allow ourselves a slightly better scenario where for a lower task complexity, we record more neurons. We should get lower distortion relative to what we would get if we recorded all the neurons if we look at all the neurons that we did record. And then the isocontours would again be straight lines, okay? So basically, this is the prediction that random projection theory makes, is you just take the data and you plot the distortion in the PCA trajectories relative to what you would get if you kept all the neurons, and the isocontour should be straight lines. Okay, so this isn't an empty test of Baraniuk's theorem, right? Because the applicability of this to neural data depends critically on the assumption that the neural manifold is randomly oriented with respect to the single neuron axes. So if we do this test in the data, we're not, of course, testing a mathematical theorem, we're testing the conditions for the applicability of that mathematical theorem to neural data. So it's a non-trivial test. And remarkably, it worked out well. So this is neural task complexity on a logarithmic axis. This is the number of neurons on a linear axis. And as you can see, the isocontours of distortion are indeed straight lines in this axis. So what this is saying, essentially, is the monkey's representation of movement in the brain is a low-dimensional manifold because the movement's low-dimensional. That's not surprising. But the manifold does seem to be randomly oriented enough with respect to the single neuron axes that the predictions of electrophysiology as random projections seem to hold. Okay, so that's actually fantastic news for experiments going forward because it's allowing us to design experiments in the future by telling us that the number of neurons we need to record going forward need only grow logarithmically with the neural task complexity measure that we've defined. So it provides guidance for the design of future experiments, which is very exciting, especially at a time when there's such a huge emphasis on various national brain initiatives to record more neurons. Okay, so okay, fantastic. So let me summarize. So everything that we've been doing is for trial average neural data, where we've been talking about trial average neural manifolds. And we found that under subsampling, we can accurately recover these dynamic portraits, and we don't need to record that many more neurons. And the complexity of the task does indeed upper bound the dimensionality of the data in a way that can now be precisely quantified. Okay, but what about situations where we start moving to more and more complicated tasks where the monkey can be moving its arms around in very complicated ways so that the behavioral states of the monkey are never revisited twice? Okay, so then you just cannot average the neural data because you can never condition on the monkey getting to the same point in behavioral space many, many times so that the preconditions for averaging are allowed, right? So we need to think about single trials, right? So we've started thinking about various toy problems to figure out how many neurons you'd need to record to accurately recover structure and data on single trials. So the simplest scenario you could possibly imagine is you could imagine a scenario where you could imagine now a sensory scenario where you show P stimuli to the animal. And for whatever reason, these P stimuli might be embedded in n-dimensional neural activity space within some kind of linear k-dimensional subspace. And of course, if it's a nonlinear manifold, if it's not too curved, then a not too curved nonlinear manifold lives within a low k-dimensional subspace, okay? But again, the problem is we don't get to observe the full n-dimensional space or 100 million dimensional space of all neurons. We see a shadow of that space, and the neural activity patterns are corrupted by noise. So we see these noisy patterns on a shadow of the full manifold. So these are the parameters: the total number of neurons, the number of neurons we record, the dimensionality of the subspace, and there's a signal-to-noise ratio reflecting trial-to-trial variability. So natural questions to ask are, for what regimes of these parameters, M, N, P, the number of stimuli you get to see, and the signal-to-noise ratio, can we correctly recover the subspace, its dimensionality, and then accurately decode on single trials, on held-out data, the stimulus, okay? So this actually leads to interesting random matrix theory problems because you can formulate this as a low-rank matrix denoising problem where the signal matrix has an interesting property. So you have a k-dimensional stimulus and p stimuli, so they can be parameterized by a k by p matrix. They're embedded into neural activity space by k columns of a random unitary matrix. So again, we're assuming random orientation of the subspace. But again, there's a projection operator, which is an m by n projection operator that picks off M neurons. And there's also observational noise, right? So what's relevant is the product SU is a corner, an M by K corner of an N by N unitary matrix. This product SU is what's making X invisible to you. So we have to think about the spectra of corners of random unitary matrices. That becomes actually now relevant for thinking about how many neurons you need to record. And then we can plug into existing, and then also there's a lot of work understood about perturbations to low-rank matrices by random Gaussian matrices. And so then there are results on how well you can recover the matrix X, right, or the subspace. And there are phase transitions in your ability to recover the singular values and singular vectors of X as a function of the amount of data that you observe. And those depend, again, on the spectra of these, you have to compare signal singular values to noise singular values, roughly speaking. So we worked out using free probability theory the spectrum of the corner of a random unitary matrix. It has some interesting structure, and in fact, we can compute the minimum and maximum singular values for a k-dimensional subspace projected down to an m-dimensional subspace and an ambient n-dimensional subspace. And we get actually, at the end of the day, a very simple result, which in the relevant regime for neuroscience is the signal-to-noise ratio times the square root of the number of recorded neurons times the number of stimuli that you show better be bigger than k. And if you're on the correct side of this phase boundary, then everything works well. You can infer, so this is an example of the phase boundary for a situation where you have 5,000 neurons in a 20-dimensional subspace. And on this side of the phase boundary, you recover correctly the dimensionality. And then subsequently on this same side of the phase boundary, you can do single trial decoding accurately on held out data. Okay, we've extended this also to dynamical systems, and this leads to an interesting result where, let's say now you have a dynamical system, right? You have a high-dimensional neural circuit with n neurons, but again, you can only record m of them for a finite amount of time t. What can we correctly infer about the dynamics of the circuit when m is much less than m is much less than n, and t is not too large? And in general, of course, the answer is absolutely nothing, right? However, if we assume some kind of underlying simplicity, for example, low-dimensional dynamics of the circuit of dimension k, then maybe for certain regimes of m, n, t, and k, we can correctly recover dynamical properties of the circuit. So a very simple thing that we can do is we can work out the theory for a linear neural network and then apply it to nonlinear neural networks. So what we do is we imagine a linear neural network with a low-rank connectivity matrix where the eigenvectors of W are incoherent with respect to the single neuron bases. They're essentially random eigenvectors. So we have a rank K connectivity matrix. This forces the dynamics of the system to approximately lie within a K-dimensional subspace, and we record a random subset of M neurons. Now this leads to an interesting random matrix theory problem where the data matrix, which is the M by T matrix of observed neural activity, has correlated columns. The columns are correlated because even if you feed a linear dynamical system with white noise, the activity at different points in space and time are correlated because of filtering through this recurrent connectivity. So we analyze the performance of a particular algorithm called subspace identification, and we find, let me just give you the final answer. So again, we can formulate the recovery of the eigenvalues and eigenvectors through a matrix denoising framework. But of course, we have to worry about the noise now, right? So this is an interesting situation where this is a usual Marsenko-Pasteur distribution if there were no time constant here and you were just looking at white noise. But if you now have a non-trivial time constant, the correlations between the columns ups the maximal singular value of the rectangular matrix with correlated noise. And we can exploit results from recent work in random matrix theory that tells us how to compute the singular value spectrum of random matrices with correlated columns. So the correlations impede your ability to recover the dynamics of the circuit, but not by too much. So at the end of the day, you have, again, another type of phase transition that's, again, inherited from these singular value and eigenvalue phase transitions of low-rank of perturbations of low-rank matrices by random matrices with correlated columns. And essentially, you find that in a system with 5,000 neurons, maybe a 6-dimensional subspace, this is our theoretically computed phase boundary. And we find that if you're on the wrong side of the boundary, you get the inferred dimensionality wrong. but if you're on the correct side, you get it right. And moreover, if you're on the correct side, you get the eigenvalues, or essentially the spectrum of time constants in your circuit correct. But if you're on the wrong side of the phase boundary, you get them wrong. So I think there's a lot of room for interaction between high-dimensional statistics and neuroscience to give us some kind of theoretical or conceptual clarity on when we can and cannot do certain experiments. And so we've now recently extended this work to curved manifolds and so on and so forth. And we've actually tested some of this on single trial data from the Matteo Carandini lab that looks at visual cortical data. I don't really have time to talk about that. So that's sort of, we're playing around with the single trial stuff now, but let me thank people. So, good, okay. So this work was mostly done by my graduate student, Peiran Gao, and also Eric Troutman in the Shenoy lab. We collaborated with the Shenoy lab on the motor cortical data, which was a lot of fun. And I'd like to thank my funding sources. Thanks. Yeah, Alfred.
One basic question, and that is the effect of the electrode-induced degeneration of neural.
Oh, yeah. We actually have written a paper on that. Yeah. So all of the data that we analyze, are from within day data, right? So within a day, the electrodes are stable. However, in applications to brain-machine interfaces, you lose electrodes over multiple days. And actually, you can combat that very simply. In a brain-machine interface, don't decode off the neural data, but decode off the principal components of the neural data. And essentially, what that does is it makes you more robust to single neuron loss. We have a paper on that demonstrates that type of regularization makes you more robust to single neuron loss. Because essentially, by projecting to the principal component basis, you're effectively filling in neurons that you lost. But this data is not subject to that issue because it's within day data. Exactly, yeah. Short, like a few hours, but not that short, yeah. Uh-huh. For at least recovering the correct state space dynamics of the circuit, after which you make scientific inferences from that state space dynamics. Oh, this is an interesting question. Okay. So why is the brain organizing itself so that it's low-dimensional, randomly oriented, right? I think it's because there's an alignment of goals between the neuroscientist and a downstream neuron, right? A neuroscientist has to stick 100 electrodes into the brain and decode the contents of that brain circuit. Of course, the brain doesn't care about a neuroscientist being able to decode it because neuroscientists came along after the brain evolved. But it does care about a downstream neuron. A downstream neuron gets to send 10,000 synapses into the upstream brain region, and using those 10,000 synapses, it has to do whatever computation it needs to do. So the neural circuits need to organize themselves so that 10,000 measurements are enough. Now, for the simple tasks that we're doing, 100 measurements are enough. But you could imagine that as you go to more and more complex tasks, you might need to increase the number of neurons. So in that sense, 10,000 provides an upper bound in some sense that we haven't really worked out precisely on the complexity of behavior that could be implemented and still be able to do computation in a circuit with limited degree connectivity. Yeah, that's an interesting theoretical problem, which it's on the back burner at the moment.